Hello, good morning, everyone. So today we will start something new. We will talk about probabilistic methods. But before we do so, let me talk about something that appears in the lecture note 16. So we will introduce the so-called random graph model. So random graph model is something that we can help to analyze the property of certain graph algorithms. So here, this random graph model is going to define a certain probability space, a sample space, so that we can generate normally undirected simple graphs with n vertices. So there are two common models we are using. The first one is called the Gnp model, and the other is called the Gnn model. So what is Gmp model? It's a very simple concept. So Gmp model is going to generate a random graph with exactly n vertices. And the p here denotes the probability that whether we will find two vertices, a certain two vertices having an edge. So Gmp models generate a graph so that each edge will appear with probability p independently. So in that case, for a particular set of m edges that we hope the graph to generate, then the chance of this to happen will be equal to, for these m edges, we hope that they are generated, so there is p to the power m chance. And then at the same time, for all the remaining edges, for all the remaining n choose 2 minus m edges, so this big M minus little m edges, we want them to not appear. So we should multiply this with the probability 1 minus p to the power all the edges minus m edges. Is that okay? So GMP will have a sample space of how many graphs? So in this GMP model, we will have this M, big M is the maximum number of edges, or the number of edges in the complete graph with n vertices. So the total number of graphs that GMP can generate will be 2 to the power this big M. Is that okay? Yeah, because for each edge, it is either there or not. But then, not every graph will be generated with the same probability. Some will be more, some will be less. Is that okay? So for instance, the graph that has all the edges will be generated with probability p to the power big M, and the graph with no edges will be generated with probability 1 minus p, this number to the power big M. Okay, so this is the GMP model. So one way to generate a random graph in this model is we start with an empty graph, and then for each edge, we pick it randomly, independently with probability p. Okay, the other graph model is called the Gnn model. Now, Gnn model is still generating a graph that has exactly n vertices, but then this big N here denotes the number of edges that will appear in the graph. So we will always have exactly big N number of edges. So to do so, it is simple. So we first start with an empty graph, and then we select one of the edge randomly. And if it is not there, we will select that. And then among the remaining possible places that we can place an edge, we will select one of them randomly, and then check if it is, yeah, and then we add it, and so on and so forth. So we do this process until we have exactly n edges, and then we will stop. So how many graphs are there in this GNN model? So it is no longer 2 to the power big M, but instead it is going to be big M choose big N. Okay, so because out of these big M edges, we need to select which big N edges we should be using. Okay, so somehow this GMP model and the GNN model is similar to the Poisson case and the exact case in the balls and bin. For instance, GNN is the exact case because we will always have exactly big N edges. And then GMP, if we set the little p correctly, then we will have expected big N number of edges. But then GMP will be the Poisson case because every edge will appear independent of each other. Now this big N is not. Okay, so we are now, this is all we need to understand the topic for today. Okay, so this is the random graph model. Okay, so let us take a look of today's lecture notes. So we will talk about lecture note 17, and then we expect that there is also time left. We will also start a little bit of the related topic in lecture notes 18. Okay, so the topic for today is called Probabilistic Method. So what is it about? So it is really unlike the discussion so far that we are aiming at this developing an algorithm. So here, our purpose here is to use probability to help us to show that something must exist. Okay, so purely it is a mathematics problem. But then, of course, something that is existing could be then used as a good fact for us to design an algorithm. But then the main purpose for probabilistic methods is to show something exists using probability. Okay, the main idea here is that if a certain object can be selected from a sample space with positive probability, so we don't care whether this probability is close to 1 or not, as long as it is greater than 0. Then what does that mean? It means that such an object must exist. Yeah, otherwise the probability should be exactly equal to 0, right? So if something can be selected with non-zero probability, then it means that such kind of object must exist. So we are going to use this way to prove existence of things. And then we will talk about two techniques today. One is called the basic counting, and then the other is called expectation formula. But then we will have other techniques that to be discussed in the next class. So basic argument, counting argument. So let's see an example of how we can use this idea, basic counting, just simple counting, to help us to show existence. So let's take a look at this problem. So we want to ask, is it always possible, okay, to color the edges of a complete graph in red or green so that we don't see any click such that all the edges are with the same color? So we are introducing this word called monochromatic. Mono means one. Chromatic means color, so it is a single color. Click means that a complete graph. Okay. So let us recall a very famous problem that we have studied in the discrete mathematics class. So we have 6 people, and then between any 2 people, they are either friends or they are enemies. So for these 6 people, we can see that there must always be either we can find 3 of them, they are mutual friends, or we can find 3 of them, they are mutual enemies. So we cannot escape this fact. Either there must be 3 mutual friends, and if it doesn't occur, then it means that there must be 3 mutual enemies. So this is one of the problem, the special case here. So can we color the edges of a complete graph with 6 vertices in red or green? Red, let's say, represents enemies. Green, let's say, represents friends. So that we do not see any monochromatic triangle. So if you imagine, as we increase the number of vertices, then there will be more and more edges in the graph, and then it is now more and more difficult to avoid certain things to happen. So here, this is a similar problem, except that we are talking about generalized click, and then we may need then a larger graph. Okay, so I hope you understand what is going on so far. To fix our notation, we use n to represent the number of vertices in the graph, and then we use big Kk to represent a complete graph with k vertices. Okay, so the intuition here is that if n is very large, then it is more and more difficult to avoid a red KK and a green KK at the same time. So that means that when n is very, very large, then we must either find a red KK or a green KK. So this is the theorem that we are going to show if this condition is met. So what is this condition? This condition is, it's like n choose k, and then this is 2 to the power k choose 2, right? So here we will see that for a fixed k, as n becomes larger and larger, this whole thing will become larger and larger, right? When k is fixed, then this number should be increasing as n goes up. So that means that if this condition is met, then the value of n is not that large. Okay, so if n is not that large, then it is possible, so we are going to show that it is possible that we can color the edges of the complete graph with n vertices such that we can avoid a red KK, and at the same time we can avoid a green KK. Okay, so instead of showing that n is large, we cannot avoid, here it says that when n is sufficiently small, then we can really avoid a red KK and a green KK at the same time. So far, let me check if you are okay with the problem definition. Let me see. Okay, so far so good. Okay, and let me know if you have any questions, okay? Okay, so what we are going to do here is, let us define a sample space. So what is going to be our sample space? We let S, the sample space, to be all the possible colorings of the edges of Kn. So Kn has many edges, okay? So each edge can be colored in red or green. So all of them are red is one case, all of them is green, it is another case. The first edge is red and all the remaining is green, it is another case. The second edge is red and all the remaining edges are green, it is another case, and so on and so forth. So there are going to be 2 to the power n choose 2. So how many edges are there? There are going to be n choose 2 edges. So for each edge, there are 2 ways to color. So in the sample space, we have 2 to the power n choose 2 colorings that we are going to consider. Okay, and so once we have this coloring, we are going to choose one of them at random. So by choosing a graph randomly from this one, then we are fixing that this graph will have a specific coloring, and then this graph will have n choose 2 edges. Is that okay? So how can we select such a graph? It's actually simple, like the Gmp model. We will start with an empty graph, and then we will color each edge in red with probability 1/2. So otherwise, if it is not red, then it is green. Okay. So it is actually a Gn 1/2 model. Okay. Now, let's take a look of such a graph that we are selecting. Okay. So we are selecting a random graph, right? Now, we want to ask, inside this random graph, okay, whether we can find a monochromatic clique with size k. Okay. Now, if we fix a particular set of k vertices, so all the graph has n vertices in total. But if we fix a particular set of k vertices, we hope that it is monochromatic, then there will be how much chance are there? We need all of the edges inside this k vertex clique to be all red or to be all green. So there are 2 ways that we can do so, and each way appears with probability 1/2 to the power k choose 2. Is that okay? So perhaps, yeah, I think, yeah, let me write a graph. Perhaps it's easier to demonstrate what I'm saying. Yeah. Okay, so what does that mean? So what I'm saying, so here we are having a very large graph, maybe this one. Let me do this. Okay. So let's say we have a large graph that has many vertices. So this is another vertex, this is another vertex, this is another vertex, and so on and so forth. And so forth. So there are many vertices. Now suppose that we are focusing on a particular set of k vertices. Let's say, what should I use? Perhaps this. Okay, so let's say this is a set of k vertices. I don't know, yeah. This is the set of k vertices. We want to ask, what is the chance that this set of k vertices will form a monochromatic clique? So in that case, we need this edge to be of the same color as this edge, to be of the same color as this edge, and so on and so forth. So inside this clique, so it may not be monochromatic, but then this clique will always have a k choose 2 edges, right? So we need it to be monochromatic. It means that either all the edges are colored red or all the edges are colored green. Now the chance that all of them are red is 1/2 times 1/2 times 1/2, and so on and so forth, up to k choose 2 times. Similarly, the chance that they are all green is 1/2 times 1/2 times 1/2 times 1/2, and so on and so forth, up to k choose 2 times. So the chance that we will see a monochromatic clique among this particular set of k vertices, it is equal to 1/2 to the power k choose 2 multiplied by 2. So this is the number that we have here. Okay. Okay, now, then what is next? Okay, now, this is the chance. So previously, this is the chance of having a particular set of k vertices to be a monochromatic clique. Okay, now let us take a look of how many ways can we choose k vertex inside this Kn graph. Okay, so how many ways are there? So there are n vertices in total, and then if we want to choose a particular set of k vertices, then there are n choose little k ways. So this x value is equal to n choose k. Is that okay? So here we let A to be the event such that there is a certain there is a k vertex. Okay, so here there's something wrong. Okay, so let A be the event that there is a k vertex monochromatic clique in Kn, and we let A1, A2, A3 up to AX be the events such that the jth k vertex clique is monochromatic. Is that okay? So A1 focus on the first way of selecting k vertex, A2 focus on the second way of selecting k vertices, and so on and so forth. Now probability of big A is there is a k vertex monochromatic clique. So for this to happen, either A1 happens or A2 happens or A3 happens, and so on and so forth. So A is equal to A1 union A2 union A3 up to union AX. And by union bound, we see that this probability is less than or equal to the summation of all these probabilities. Okay, and then each one of them is symmetric, so the chance of A1 to occur is equal to the chance of A2 to occur, and so on and so forth, up to the chance of AX to occur. So there are X ways, and then each of them is the value that we have computed just now. And because X is equal to what? N choose K, right? So we can replace this as N choose K, so we will have this one. And now, this is the magic term that appears in our theorem. So our theorem has an assumption that this value is less than 1. So what does that mean? So it means that the probability of A happening is less than 1. So the chance of having a monochromatic clique is strictly less than 1. So the complement of A will be strictly greater than 0. So what is the complement of A? The complement of A means that you do not see any monochromatic clique. So we are done. So in that case, the complement is the case that we don't see any monochromatic clique, and then it is greater than 0. So by this argument, we have proven that there is a way to color the graph such that we don't see any monochromatic clique. Okay, although we don't know how to color it, but then we have actually shown that it must exist. Okay. So for instance, yeah, this is a case. Suppose that we have a group of 1,000 people. Is it possible that for any 20 people selected, some pair of people will know each other when some people don't know each other? It means that it is not the case that all the people know each other, and it is not the case that all the people don't know each other. So for any 20 people, some of them knows each other and some of them don't know each other. So we are plugging in the formula. So this is the n that we have, and this is the k that we have. So by plugging in the formula, then we can verify that the magic term here that we have really is less than 1. So we are done. Okay. Okay, this problem, yeah, so this is the case. Yeah, so it's straight less than 1. So the answer is yes. And this problem is related to an interesting branch in mathematics called Ramsey Theory. So you can check it from the Wikipedia. So this theory studies the opposite part. So it wants to find out what is the minimum n to guarantee that we can no longer avoid the monochromatic cliques. So what is the minimum n such that when we color the Kn edges in 2 colors, we must either find a red R clique or a green S clique. So we don't need this R and S to be the same number. So we are using little k for both of them in our example, but here we can have R and S here. So such a number is denoted by the Ramsey number of R and S. So for instance, you can easily show that in order to avoid, okay, so if you really want to avoid any red clique with 2 vertices, so any red edge, and any green clique with S vertex, then we cannot have the graph to be very large. As long as the graph has S nodes, then we cannot avoid a red edge or a green clique. Reason is, if the graph has exactly S edges, S vertices, if one of them is red, then we are not avoiding a red. In the other case, all of them are not red, then in that case, we are not avoiding a green. So we will have R of 2S will be less than or equal to S. But on the other hand, we know that if we just have S minus 1 vertex, we can color all of them, color all the edges in green, so that we are really avoiding everything. So we will also see that the Ramsey number of 2S is strictly greater than S minus 1. So in that case, we can compute that R2S is equal to S. And the famous example we have just mentioned today is we want to avoid red triangle and a green triangle, and then if we have 6 vertices, then we cannot avoid them. Okay, but 5 we can. Now, so although it looks like so the difficult part here is that in order to find out RRS, we will need to know the upper bound and the lower bound at the same time, and then they need to be tight in order to get the equal bound. Okay. So it makes the problem of computing the Ramsey number of RS very difficult. So a mathematician called Paul Erdős, he told us how difficult this problem could be. So he says that imagine we have an alien force very powerful, and then this alien force asks us to find out the number of R55. So if we can find out this number, they will let us go. Otherwise, they will invade us and destroy our planet. So if they request us to find out R55, perhaps the best way that we should do is we should gather all the computing powers and then all the smart people or whatever, to find out what is the exact value of this R55. But on the other hand, if the alien now requests us to find out R66, then in that case, he says that there is no chance that we will be able to compute this value. And then so we should really fight back the alien, whether or not we have any chance to win. Okay, so R55, R66, these values are still open. Nobody knows. Sometimes we can have upper bound, sometimes we can have lower bound, but then these bounds are not matching. So nobody knows the exact value of these terms. Okay, so the previous part is the so-called basic counting. So here we are just counting, yeah. So what we were doing, so counting how many ways of doing something, and then also counting, yeah, how many possible cases could occur, and then here this is the union bound, and that's it. Okay, and then the second technique that we are going to introduce is called the expectation argument. Okay, or sometimes this is called the averaging argument. Let us take a look of these two formulas. So they look really similar. Okay, it says that the probability of x greater than or equal to the expected value of x is always greater than 0. So this is actually a fact. This is actually a theorem or fact. For any random variable x, the chance that x is greater than or equal to expected of x has to be non-zero. And similarly, the chance that x is less than or equal to the expected value of x has to be non-zero. Okay, the proof is really easy. We can prove it by contradiction. Remember, the equal sign here is important, so we must include the case that x is equal to expected of x. Okay. So here, this is so this is exactly the same. Probability of x greater than or equal to the mu expected value of x is greater than 0. So we prove this by contradiction. If it is not greater than 0, that means that it must be equal to 0 because it is about probability. So the probability of this is equal to 0, and then we hope to derive something wrong. And now let us find out, based on the definition, how the expected value is computed. The expected value is computed by summation of all the possible cases of x weighted by the chance that the random variable x is equal to this value of x. And then, because the case that the chance of the random variable x greater than or equal to mu is equal to 0, so this summation can focus on all the values of x where they are strictly greater or strictly less than mu. Okay. But then in that case, we will see that, so this is going to be equal. So we are ignoring the case where the little x is greater than or equal to mu. Yeah, it is equal, okay? But then in that case, this little x is always less than mu, so this whole summation sign is less than if I replace this little x by the mu value. But then this mu is now independent of x, so we can take it out. Summation of x is less than or equal to 1, so in that case, this is equal to mu. So mu is strictly less than mu, so it is impossible. So we can prove the other sign using exactly the same way. Okay. Okay, now this is a very simple observation. So we are going to use this to get some interesting result. Okay. So we will look at this problem called large cuts. Okay. So first of all, we have a graph. This graph is unweighted, and then and then let's say this graph is also, we have a simple graph. Okay. So we want to find out, is it possible to delete some number of edges so that the graph becomes separated? Okay, if this is the case, the edges that we are deleting is called a cut. So formally, a cut is a partition of the set of vertices into two groups. Let's call it V1 and V2. And then we count. So we are putting into, okay, so this is called a cut. So a cut is a separation of the vertices into two groups. But then the size of a cut is talking about what? It's talking about what are or how many edges are there such that one vertex is from V1 and the other vertex is from V2. So in such a case, then this is called the size of a cut. And then it turns out that finding a cut that has the maximum size inside the graph is NP hard. Okay, so let me make a correction here. So it turns out that, okay, for this particular problem, we really want to find, so we really want to divide the vertices into two groups such that there are many edges across the two groups. So whether or not the graph is disconnected at the beginning or not, it doesn't matter. So we want to find out a way to make sure that we can have a lot of edges between the two groups. And so this is called the large cut problem. So let me check if we are all okay with the definition so far. Okay, so far so good. Good. Okay, so what we are going to do here is it possible for us to get, so because this is already an NP hard problem, so it means that so far there is no efficient polynomial time way to compute the maximum size cut. So instead, is it possible that we can get a suboptimal cut easily? And then we hope that this suboptimal cut is not too far away from the optimal one. So can we have an suboptimal cut that has at least half the size of the optimal one? So here we are going to do so with a randomized algorithm, but then later we will turn this randomized algorithm into a deterministic algorithm. So our target here is not to find the optimal, but to guarantee to find some solution such that it is at least as good as half of the optimal. Okay, so one thing that we need to observe, or is simple observe, is suppose that the graph has m edges, then any cut size cannot be greater than m. Yeah, because these are the most number of edges that we can have across the two partitions. Okay, and then so this is an upper bound of the size of a cut. And now we have a theorem that talks about the lower bound of a maximum cut. So if the maximum bound, we know that it's m. Is that okay? This is the total number of edges. But then we can also know that there must exist some cut whose size is m/2 or more. So we are going to show this lower bound is true by using the expectation argument. So what we are going to do here is, let us construct a random cut. Okay, so recall that a cut is a partition of vertices. So we construct a random cut by assigning each vertex randomly in V1 or V2. Okay, so that means that for each vertex V, the chance that it is in V1 will be equal to the chance that it is in V2, and it is equal to 1/2. So we let big X to be the size of this cut, and then we can easily compute the expectation of X. So how do we compute this? This is by linearity of expectation. Okay. So first of all, let us define x1, x2 up to xm to be indicators such that this is about the first edge, this is about the second edge, this is about the mth edge. So whether the first edge will be in the cut, or whether the second edge will be in the cut, or whether the mth edge will be in the cut. Okay, so xj is equal to 1 if the jth edge has one endpoint in V1 and the other in V2. Now for all these xi values or xj values, we know that the expected value is exactly 1/2, because there is 1/2 of the chance that, so let's say we select one endpoint in some partition, then there is half of a chance that the other endpoint will be in a different partition. So the chance that the edge will be across the cut will be selected as the size of the cut inside the site with probability 1/2. So the expected value is 1/2. Okay, this is an indicator. Now the big X that we have is simply the summation of all these indicators. Yeah, we know this already, right? This is a simple observation. So by linearity of expectation, expected of x is equal to m times the expected of x of 1, so it is m over 2. So it means exactly that the maximum cut, we know that it cannot be greater than or equal to, it cannot be greater than m, but on the other hand, the maximum cut will always still be greater than or equal to half of m. Okay. So here, so because of this, then let's see if we can have a way, an algorithm to get a cut with size m over 2. So what we are going to do here is we use the same process as before. So we are going to use this process, randomly assign the vertices in one of the V1 and V2. Okay. So we will see that, suppose that x is the size of the random cut. So sometimes it could be bad, right? But then sometimes it could be greater than or equal to m over 2. So we define the probability of success is as long as we get the size to be greater than or equal to m over 2 in the random cut, then we will say it is successful. Otherwise, we are saying that it is failing. Okay. Then let us see the relationship between this p and this m over 2. So first of all, m over 2 is equal to the expected value of x. We know this is true. But then expected value of x can be separated into the summation of x multiplied with probability of x for x in two different ranges. One is x is less than m over 2. The other case is x is greater than or equal to m over 2. Is that okay? Now we will see that, okay, so each of these terms, we can replace them by using p and then m. Okay, so for instance, in this case, the value of x is less than m over 2. So it means that the value of x is at most m over 2 minus 1. And the total probabilities that we are talking about here is the case that we are failing. So it is 1 minus p. Is that okay? So the left term, the first term here, that we can see it is strictly, or it is smaller than or equal to 1 minus p times m over 2 minus 1. Is that okay? And similarly, the value of x here, although it can be unknown, but then we know that it is upper bounded by m. And the summation of the probabilities here is equal to p. This is the case that it is successful. So we have this relationship. Then in the case after rearranging the terms, this p is the probability of success, right? So by rearranging the terms, we can move p on one side and then move the other terms on the other. So we will have p greater than or equal to 1 over m over 2 plus 1. So in that case, even though we are doing a random assignment, there is still roughly 1 over m chance that we can get some assignment that is good enough. So by repeating doing this random assignment again and again, then we will have more and more chance of getting a cut that is what we need. So by roughly running this algorithm for something like m log n times, then it will be nice. Okay. So this is the first example. So in this example, not just we show existence. So we show that existence of a cut with size at least m over 2, but then we are turning this into a randomized algorithm, and then we can analyze the probability of success. Okay, similarly, we will have another example. So this is called the max set problem. So in the max set problem, we are given an SAT formula. Okay, let's say this is in the so-called conjunctive normal form. So it is like many clauses and together, and then within each clause, it is just some variables or the opposite of the variable all together. So each of them is called the literal all together. So this is a clause, this is another clause, this is another clause. So there are 3 clauses and together. So we have the input of a certain formula like this, And then our first target is to check whether it is satisfiable, whether we can select some assignment for x, y, z, and so on and so forth to be either true or false, so that the whole formula is true. But then this problem is NP complete. To decide whether a formula is satisfiable is NP complete. And so we can also define a certain, so this is a decision problem, okay? Decide whether it is a yes or a no for the answer. But a related problem called max set is we are still given the same formula as the input, but in that case we do not need to make sure every one of them is going to be true. But still we want to find out an assignment of x and y and z to be true or false and so on and so forth, so that we can have many clauses to be true. So what is the way to maximize the number of true clauses? Okay, and then this problem is actually even harder than this checking of the SAT formula, because if we know how to solve this maximization problem, we can use the result to give us the answer for this decision problem. So that's why this problem, the max set problem, is an NP hard problem. And because it is NP hard, so far nobody can give us a deterministic polynomial time algorithm for solving this. Okay. But yet, we still want to do something about this, or to observe some property about this max set problem. Okay. So similar to the large cut problem here, we do not find an optimal assignment. We want to get an assignment such that it is good enough. Okay. So suppose that there are m clauses to begin with in the formula. So in this example, there are 1 clause, 2 clause, 3 clauses. Okay, so there are 3 clauses in this example. So suppose that there are m clauses in the formula. We know that the maximum number of clauses that we can satisfy is at most m. But then how about the lower bound? So here we get a lower bound. So it says that suppose that we let k to denote the number of literals in the smallest clause, so in the shortest clause. So for instance, there's 1 literal here, there are 2 literals here, there are 3 literals here. Okay, so this is the shortest one, so it has just 1 literal. Okay, so it says that there is an assignment that satisfies at least these many number of clauses. Okay, now it says that, okay, the proof of this one is left as an exercise. So let me give you a hint. You can really work it out. Yeah, so I will give this as an exercise problem. The way here is we're using an extremely similar method as we do for the large cut. So in the large cut, we are doing what? We are partitioning the vertex into 2 groups, so that each vertex has the same chance to be in the first group or the second group. And how about this one? Can we define a certain probability space with some random assignment? Okay, so what are the things that we can randomly assign? And then for each of the random assignment, what is the expected number of clauses that we can satisfy? So this is enough enough hints. So it's enough for you to come up with an answer for this one. Okay. So based on this, we can find out this, and then we can similarly analyze the probability of success if we continuously, if we get a random assignment of whatever, and then whether we can have this result. Okay, so this is 17. Okay. Why we can assume? Okay. So here, this random assignment is our choice. So we are not assuming this. We are really actually doing this. By having this as our choice, then we can have some property of selection. Is that okay? So you can also do some different assignments. Sometimes maybe you assign V in V1 with probability 1/3, V in V2 with probability 2/3. It's also possible. But then the effect will not be as good as we are using something like this. Is that okay? So this is a way that we can do random assignment and see the property. Okay, does that make sense? Okay, so let's see. Yeah, let me know if you have further question. But let's see. So we have the large cut problem, right? And that sorry, we have the max set problem. Actually, we have a randomized algorithm for them, but actually for these two problems, we can turn the randomized algorithm into a deterministic algorithm. So we are going to talk about something called de-randomization, making something randomized into not randomized, into deterministic. Okay. We are going to use conditional expectation to help us to make our decision. So here we are going to use this to give us a deterministic way to construct a certain object with some property. So we use the large cut problem. Okay. So at this moment, what we know here is that we know at least we can find a certain cut that has size m/2 or more. Okay. So this is not going to be the best max cut, there large cut, yeah, because there's no guarantee, because there could still be something like m. So we call this an approximate large cut. But previously, we have a randomized algorithm to get a cut with this property. So now let us make the algorithm deterministic, no random involved. So let's see the example. Okay. So we have the major idea here first. Okay. So our algorithm will partition the vertex, each one v1, v2 up to vn, into two partitions randomly. Let's say one of them is A, the other is B. So we call it v1 and v2 here, right? Okay, so but here we now call A and B. That's the same. Okay. Now if we put the vertices randomly in A or B, A or B, A or B, and so on and so forth, the expected size is m/2. So, but then with the loss of generality, we know that if we initially fix v1 in A, we will also have the same property because v1 is in A, so we don't affect the expected value for each edge to be in the cut or not, right? Just assume that v1 is in A, we can start with this one. Now we can consider the two cases how the second vertex v2 is placed. Now if we know v1 is in A, then we can actually compute this value. What is the expected size of the cut if we know that v2 is in A? And what is the expected size of a cut knowing that v2 is in B? Okay, so how do we know this? So let's see an example here. So let's say we have a bunch of vertices, and then somehow we have excuse me, I'm in a class. Okay, so let's see we have a partition here. For instance, let's say we have a partition here. Let's say this is the vertex v1. Okay. Let me give it a label. Yeah. So let's call it v1. Okay, so this is the vertex v1. Okay. Now, if I know v1 is here, then we put the vertex one by one. Maybe we have some random vertex. This vertex may be put it here. This vertex may be put it here, and so on and so forth. Then we will know that if there is ever some edge joining two vertices, okay, this edge will appear in the cut with probability 1/2. Is that okay? Because there is half of a chance that this is here, half of a chance that this is here, half of a chance that this is here, and half of a chance that this is here. So in that sense, half of a chance that these two vertices are in different partition. So in that case, the edge will be there with half of a chance. But on the other hand, let's look at, let's say we have another vertex, let's call it v2. Okay, so let's say this is v2. Okay, and let's say there is an edge. Suppose that there is an edge joining v1 and v2. So there is an edge joining v1 and v2. Now, if we know that V2 is in the same partition as in V1, then the edge will not be in the cut. But on the other hand, if V2 is in a different partition than V1, then this edge will be in the cut. So if there is an edge here, so previously each edge has half of a chance to be in the cut. But in this case, if there is an edge here, then this edge will be in the cut with probability 1 if V2 and V1 are in different groups, but then this is going to be 0 if V1 and V2 are in the same group. So in such a case, this is what I want to say. Given the knowledge that V2 is in A, we can see that some of the edges are already fixed. We know that there's no longer any randomness of that. So some of the edges will never appear. But some of them will always appear. So in that case, some of them are already known. But for the remaining edges, each one of them still have a chance of 1/2 to be there. So in that case, we can compute the expected value of the size of the cut given V2 is in A. And similarly, we can compute the size of the cut given that V2 is in B. So these are something that is very simple. We can compute them in polynomial time. Just check how many edges are known, and then for all the unknown edges, whether that may still be in the cut or not, then each one of them has half of a chance. But for all the known edges, it is either 0 or 1. So we can compute these two expected values. But what do we know about these expected values? Now, by doing the expectation formula, we know that the original expected size of the cut can be expressed as the expected size of the cut given V2 in A multiplied with this probability V2 is in A plus the other term. These two terms adds up to this one. Okay, so in that case, the larger of these two values, whichever one is larger, must be larger than or equal to this one, right? Suppose that suppose that this one is larger, then we will see that the first expected term is less than or equal to the second expected term, so we can change everything to the second expected term. So less than or equal to the expected of the second term, multiply with the probability that sums up with 1. So in that case, this is a true idea. So here, what we know here is that if we put V2 in A and if we put V2 in B, we know that one of these two terms must be greater than or equal to m over 2. Initially, it is m over 2. But then if we put with extra condition V2 in A or V2 in B, one of them will be greater than or equal to m over 2. So in that case, we are going to put V2 in whichever term that makes a larger expected value. And similarly, what we are going to do next is, once we know, let's say V2 is in a certain partition, let's say B, then we will decide whether we put V3 in A or V3 in B. But we always know that one of these terms will be greater than or equal to m over 2. So in that case, we can fix V3. And after that, we fix V4, and so on and so forth. So in the end, we are going to place the vertices one by one. Each time, we put it in the place that we can have a better expected value, better conditional expected value. So once all the vertices are selected, so this is the case that all the edges are selected, then there is nothing random anymore. And then we will see that the expected size of the cuts after selection of all the vertices will be greater than or equal to the expected size of the original without any condition cut. So it is greater than or equal to m over 2. So in that case, yeah, we can get a deterministic cut with size at least m over 2. So this is how we are doing this. Okay. So this is, yeah, so the idea here is that we are going to fix the vertex one by one instead of doing them randomly at the beginning. So by fixing them one by one each time, we place it to the place that gives us a better expected value, then we will go for that one. Okay, so this is the basic idea. Okay. Okay. Yeah, I think that's all. Yeah, that's all for today. So next class, we will talk about another technique for doing this probabilistic method. So yeah, stay tuned. Yeah, we will meet again on Thursday. Yeah. Meanwhile, if you have any questions, yeah, please let me know or send it to our questionnaire form. Okay. Okay. Yeah. Thanks all for coming. Yeah. Okay. See you on Thursday. Bye bye.